All right, so I did bring up, shared the Spring 16 final exam in the shared folder. So if you have a laptop or a tablet, you can actually view that at the same time. And I'm just going to double check, make sure the recorder is on. It is in. Okay. So if you go to the shared folder for this class, the exam is already there. I placed it this morning. So, oh, maybe not. Oh, this is from exam 2. But if you go to the shared folder of cisp440, which is not the one that you have, I guess. Huh. Let's see. Okay, so the one that you have access to, I can just move it to. Let me just move the document over. Okay, so let's see, that's this one. Were you able to view the A-star trace from the other day?
Yes, but it's in another. You commented a share link.
Oh, okay. So you can have access to that one.
Yeah, but it's not the main one.
It's not the folder. Okay, let me put the link here too. So let's go to share. Because I want to share the folder itself. There we go. Here's the link. And I'll change this one to maybe just add one. That would be the best way to do it. There we go. Here. There we go. So now there should be two, shared folder links at the top part of the class, and the second one will go to the one that contains the exam, well, the practice exam. The practice exam is the actual exam from spring 2016, so this is actual. So let's go ahead and take a look. First of all, it is open book and open notes, just like your first two exams. So I would definitely strongly suggest that you prepare your material for the final exam. It's taking a little bit of time to get in. I don't know why.
Is it cumulative or is it cumulative, or will it cover just what we reviewed since the last exam?
It's going to be comprehensive, which means material from the beginning of the semester can still be included, but we weighted a lot more to the last part of the class. It's pretty hard to not exclude the stuff in the beginning, especially the set theory stuff, because we rely on that vocabulary for just about everything that we do. It doesn't seem to like it.
I'm having issues too.
Okay. Well, I can do a preview. If I open it, oh, okay. Now it's okay. Are you opening it okay now, or try to refresh it?
That's working.
It's working? Okay. So I guess it's a little hiccup on the part of the server. So basically the same thing as your previous two exams. It's open book and open notes, just no electronics. And also just like the other two exams, for things that require calculations, you just have to give me an equation or a formula that can get to the answer, so you don't have to give me the exact answers. If you want to bring a calculator, a scientific calculator is okay. Okay, that's if you think it might be helpful, no problem. Go ahead and bring a scientific calculator. Pretty much the same stuff as usual. Okay, if you want to use extra pieces of paper, bring your extra sheets of paper. Graph paper may be the most helpful because they're already in a grid format, and there are places where a grid format can be helpful. So I would use a graph paper if you have some. Just as usual, write legibly. All questions have equal weight in the case of the Spring 16 test, and I'm intending to use the same strategy here. So this way it's easier for you guys to evaluate how to prioritize the questions. because you just have to go through all of them, find the easiest one to work on first, and just work your way to the most difficult question as the last one. Okay? And the final exam does account for 40% of your final grade. Okay, so it is a bit of your final grade, but to pass the class with a grade of C, you only 37.5%. So the final exam all by itself can, in theory, be used to pass this class. All right, so getting into the questions. So the first question is based on the Dijkstra algorithm, and just in case some people do not have the Dijkstra's algorithm with them, I included the Dijkstra's algorithm as a part of the exam. So for those of you who remember the Dijkstra's algorithm, this is probably just yet another way to represent the algorithm itself. Okay. This is interesting. It says there's an error, and it's not. It's some kind of a math equation that is an error. Let me check out what it's supposed to be. I don't think I can see what it's supposed to be. I think it's a G.
G equals V comma E.
Yep. Can you see it?
I can see it, yeah.
I wonder why I cannot see it.
You're in edit mode?
I'm in edit mode, but it should still show up as, because this is Google Documents, it should still be able to do it. Let me see if I can just enter a new equation. G equals VE. Like that, right? Oh, definitely. Doesn't like that. I wonder why. Okay. It's just that one too, because these are also equations, and it doesn't have a problem with that. Okay, so anyway, with the Dijkstra's algorithm, okay, can someone tell me what is the big difference between the Dijkstra's algorithm and the A-star algorithm as far as the solution itself is concerned?
It doesn't use heuristics.
Okay, it doesn't use heuristics, but that's how it finds the shortest path. But as far as the solution, or when it's done, what it's going to give you, what is the main difference between the Dijkstra's algorithm and the A-star algorithm?
Dijkstra's finds all the shortest paths to all the vertices.
Yep, exactly. So the Dijkstra's algorithm does find the shortest path to all vertices in the graph, as opposed to the A-star algorithm, which only
Finds the one you get it.
Yep, only one single destination. Okay, so you have one single starting point and one single destination, and the A-star algorithm only guarantees to find the shortest path to that one single destination. Okay, so that's a big difference. So in this case, I changed the Dijkstra's algorithm so that you can have a set of start vertices instead of a single one. It's a very simple modification to the original algorithm. It should not be a problem. And then for each vertex in the start set, okay, I changed the distance from any start vertex to that particular vertex V to be 0. And that makes sense because all of these are in the start set to begin with. So as a result, they all have a 0 distance to a start state. Are we doing okay so far with this? So in the original Dijkstra's algorithm, there's only one start vertex. In this case, we have a set of start vertices, and they have a 0 distance to a particular start vertex. And then for all of the other ones, okay, I represent all of the quote-unquote other ones as V minus S, which contain all the vertices in V, but not the vertices that are also in S. So these are the vertices that are not the start vertices. So for all of those, the initial distance from a start state or start vertex to V is initialized to infinity, which makes sense because we do not know a path to those yet. And then what we do is we initialize Q, which is kind of like the open set in the case of the A-star algorithm. So we use V to initialize Q. So all the vertices in the graph are now in Q. And then the main loop is over here. The main loop states, as long as Q is not empty, we perform this while loop. Inside the while loop, we say, let's pick one particular vertex in Q such that this part is really just saying that the vertex that we pick has the lowest or the smallest distance compared to all of the other vertices in Q. Are we doing okay so far with these notations? Okay, because it says right here, for all W in Q, okay, so if we consider all the other, well, not all the other, when we consider all vertices in Q, the distance of V has to be less than or equal to the distance of W. So that basically means that V, the distance of V is one of the lowest within the set Q. Now there can be multiple ones that are tied, okay? If they're tied ones, you just pick one in random. Then the next thing we do is we remove V from Q, okay? So when you use subtraction, you cannot subtract an element, you have to subtract a set from another set. And that's why you see V, lowercase v in the curly brace, because you have to make it a set first before you can use the subtraction operator. And then for each E such that blah, 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 blah. Okay, so this part is really just saying for each outgoing edge from V, we want to consider a neighbor called W. Okay, so that's basically just saying, okay, consider all neighbors of V, and W is the neighbor. We want to evaluate this part here. Okay, this part is a comparison. It's comparing how far what is the distance, the total distance, going from V, which is the point that we are starting with, going through the edge that connects to W. Okay, so what is the total? If that is less than the known shortest distance to W, then we have just found a shorter path to W. If we have just found a shorter path to W, then we just update the two things that we need to know about W. The first one is what is the distance of the known shortest path to W? We just update it using the same number that we used for comparison up here. And then the second thing we also have to do is to say that, okay, the new shortest path to W is coming from V. So it's really the same thing as the Dijkstra algorithm that we talked about in class, just represented a little bit differently, because I don't use a temporary variable here called alt, okay? I just use the same expression twice. And we just go through all of these, and because every single time we go through the while loop, we are removing at least exactly one element from Q, so that means as long as Q itself is finite, this loop will end. And then after the whole thing is done, then I have this kind of strange way of ending this algorithm of creating a new graph. So this new graph has all the same vertices as the original graph, because V is still shared with the original graph, but the E is different. Okay, so this is an E prime. Okay, you may not be able to see the prime very well, but this is E prime. So E prime is a little bit different from the original edges. So E prime has all the edges that are made from the prev. Okay, so everything that we maintain here as prev will be represented by an edge in E prime. In other words, this new graph G prime is the solution graph. It only consists of the edges that are on the shortest paths. Are we doing okay so far with this? Yep.
So I'm trying to make sure here, but in our if statement, are we adding the CE, that's the current edge?
Okay, so V is the edge, V is the vertex that we have chosen to remove from Q, from these two lines. Okay? So we already know a shorter path, shortest path to V at this point. So V is known, V is already explored. But what we may not have explored are the neighbors of V. In other words, when we consider all the outgoing edges of V, the neighbors that are connected to V by those edges, those we may not have considered. So we are looking at each neighbor, the neighbor is W in this case, so we look at each neighbor or each outgoing edge from V and say, okay, since V is connecting to W through E, okay, and we know the shortest path to V has a distance of this much already, we also know the cost of the edges C of E, so when we add these two numbers, it becomes the cost of a path to W.
So that distance V isn't infinity?
It is everything is initialized to infinity to begin with, but except for everything in the start set. So all the vertices in the start set S, they are all initialized to 0. So we do have a whole bunch of at least one vertex that has a start value of 0 to begin with.
So we got that from the start set. That's what I'm trying to, that's what I was looking at.
No, the start set is only used at the beginning, right here. So this is given. The start set is given to you. Basically, I'm telling you that we are starting with these vertices. Okay? And that is used to initialize a whole bunch of vertices so that their distance to a start vertex is 0. I guess when we trace it, it'll be more clear. Is that okay? Just kind of.
What I was trying to figure out is how do we know that we're taking from the start set when we're in the loop?
When we're in the loop, we do not use the start set anymore. Because the start set is only used in this case to do the initializations. And once we have these distances initialized to 0, then we have something to start with when we pick something from Q. When we go through the algorithm, when we trace it, I think it will be more clear. Is that okay? Just kind of remember your questions for now, but let's go ahead and trace the algorithm, because when we trace it, I think it will be more clear. Okay, so if you have a mobile device or a laptop computer, you can have your screen, kind of put onto the algorithm itself, and I'm going to go through the questions so I can. Okay, so this is question 1. Question 1, it will give you a graph here, and the start set is initialized to A and D. Okay, so node A, which is this one here, and node D. Okay, when I say node, it's the same thing as a vertex because those two terms are interchangeable. So A and D are both start vertices in this case. So we have 2 places to start with. We want to use the modified Dijkstra's algorithm to figure out the solution G prime, which is, which only consists of the edges of the shortest paths. And in this case, I have a table for you to fill in. So we need to know, as you fill in the graph, I need to know which vertex has what distance and what as a previous. Yep, question?
Some question. Why doesn't this just go into an infinite loop? Because why does this actually do anything? Because if all the distances are initially initialized to infinity, then
but not all. Only the distances of non-start vertices are initialized to infinity. Okay? All right, so let me see what is the best way to look at this. Because I want to show you the graph. At the same time, I want to fill in the table. And they're all on the same sheet, unfortunately, here. Okay, I know what to do. I am going to create a new spreadsheet. And I'm going to use, kind of like display both of these side by side. And I need to unhide this thing. And resize one of the windows. So I'm going to pick this one and move it to its own window. And resize it. Where's my resize button? Okay, fine. We'll do it this way. So this way I can display the trace on one side, and then on the other side I kind of have to move this one into its own window too, because this way I can kind of scroll the whole thing to one side. So not move. I want to resize this one. There we go. Okay, and we can shrink this just a little bit. There we go. Does that work with you guys? We can look at the graph on the left-hand side and then the trace on the right-hand side. So over here, I'm going to also specify the vertices, what is the prev, and what is the dist to that vertex. And we have vertices A all the way to G, so I'm going to initialize all the vertices first. Okay, so A, B, C, D, E, F, G. Okay, we got 7, and we got 7 vertices, so that's good. We don't need this column to be that wide anymore because we need more space to kind of keep track of how prev and distance get updated. Okay, So the way I want you to trace this is to show me how you update the pref and how you update the dist of each vertex. Okay. So we start with the distance because in the algorithm we initialize all the distances to infinity except for the vertices in the start set. Okay. So the ones in the start set given in the question. Okay. So when you look at the question, A and D are in the start set. So the distance to A is 0 to begin with. The distance to D is also 0 to begin with. And I'm going to use a string thing here because I want it to be aligned a little bit differently. And we'll keep updating it too. And the prefs are all undefined to begin with. So initially they're all undefined. So we'll just go ahead and use undefined to initialize all of these. And then the distances for everything else are all infinity. So let me see if I can insert a special note function. Nope. There's no way for me to insert infinity. I'll just say I and F as for infinity. Okay, there we go. So this is basically how the two functions, quotable functions, are initially initialized. So as we go through the algorithm, we'll have to kind of pick one as the V, and then we'll use it to update the other one. Are we doing okay so far with the initialization of the pref and also the distance to each vertex? Is that okay? All right. So initially, all of these are in G. Okay. So initially, all of these are in G, and you want to be able to kind of track which one is in G and which one is not. So the way you can track that is just to put a little tick sign. If it's out of the G, you can use a tick sign to say that it's out of G at this point. Okay. So out of in the first iteration of the while loop, which one should I pick to remove it from Q, from the set Q? Because initially all of these are in Q. We can pick A. We can also pick D. Okay, so choose one. Okay, it doesn't matter which one we choose because they both have the shortest distance to a start vertex. Okay, so if I want to track Q here, I'm just going to track Q here. So initially Q has all the vertices. Okay, but in the first iteration, we'll pick one, either A or D out of it. I'm just going to pick D out of it. Okay, so D is no longer in the set. We only have A, B, C, E, F, G in it, because in this case we picked our vertex V to be D. Okay, is that okay? So once you have picked D, then you have to say, okay, let's consider all the neighbors of D, and see what we can do with those neighbors. And D has a neighbor of F. So now we have to say, okay, what is the distance to D plus the edge going to F? What is the sum? 2, because it's 0 plus 2. How does 2 compare to the distance to F at this point, according to column C?
A lot less.
A lot less, okay. So yes, it's so that means we have to update it. Okay, so now we have to go here. Yep, go ahead.
What are we comparing it to?
We are, okay, let me see if I can show the algorithm. I can't show all of them at the same time because I just don't have the real estate to do it in my browser. And let's see, where's my other browser? I think it's this one. Okay. I can open this one more time. So this one can stay on the algorithm. Okay, so we are basically, at this point, we have picked the V already, which in this case is vertex D. We have already removed that particular vertex from Q, and we are now evaluating all the edges coming out of vertex D. Okay? And this is the number that I just mentioned. The number that we just mentioned is the distance to vertex D plus the cost of the edge from D to F. Okay, let me show the graph here. So we are looking at this guy is vertex V, is V, the variable V. This is the edge that we are considering, which is E in the algorithm. So we are looking at this and go like, okay, what is the cost to get here? According to our table, the shortest path or the cost of the shortest path to D is a 0 because it is a start state, a start vertex. So we have to add this 0 to this edge cost of 2, which is a 2. So that means we have just found a way to get to F with a distance of 2. Is that okay?
Mm-hmm.
So we now have to compare that distance of 2 to the known cost of the other path, which is infinity, because we did not know a way to get to F initially. But now we do. So now we have to update two things, because now we can say, oh, we have just found a way to get to F with a cost of path of 2, and then the previous is also no longer undefined, because now we know that we can go from F through D. So this is how I want you to kind of track the updating of the of those two columns. Okay, there's no need to cross out. If you just use a comma, I understand that those are all successive updates. Are we doing okay so far? Following the algorithm. Okay. Okay. So, are there any other neighbors coming out of D? Are there any other edges coming out of D? Nope. We are done. Okay. So there's also one more thing we have to do. Oh no, this is it. All right, so now that we are done with the for loop, let me switch back to the algorithm. Yep, go ahead.
What about keeping track of
G?
Yeah, what's in G?
What's in G? You mean uppercase G or lowercase g?
Uppercase.
Uppercase G is the graph itself. In other words, uppercase G is what you see here as a graphical representation.
Oh.
So G is a two tuple. It has a B, which consists of all the vertices. So A, B, C, D, all the way to G is in the vertex in the B set, and then all the edges are in the E set.
I remember you saying we had to keep a mark in the vertex to see if it was in the set.
Right. Oh, okay. I see what you mean. So in here, we can now represent that D is no longer here. So you can just use whatever thing that you want to use to represent it. So you can say, a prime here to kind of mark it so that we know that D is no longer in the set. It's up to you. I mean, this is just a way for you to track. Okay, you can cross it out. You can just use a cross out and say it's no longer in the set Q. Or you can do it like this. Okay, so you can just kind of track it as you go through the algorithm. So there are different ways. As long as I understand what you're doing, it's fine. Okay, so now that we have 3 vertices now. No, I take it back. We only have 2 vertices with not infinity distance in the set Q. Because remember, D is no longer in Q. Okay, so that is out. So of the only 2 left, we have to pick A instead of F, because A has a distance of 0, F has a distance of 2. 0 is less than 2, so we have to pick the smallest one. Is that okay? So in the second iteration of the outer loop, A is removed, so we only have B, C, E, F, G in the set Q, because this time we have just picked A as our vertex. Okay. So once you pick A as the vertex, then you have to ask the question, what are the outgoing edges of A? Okay, so A has 2 outgoing edges, so we have to evaluate both of those. The ordering of that evaluation is not important. You can evaluate vertex C first if you want to. So let's just do that, okay? So we'll evaluate the neighbor C first, and then we have to say, okay, the cost to get to vertex A is 0 because it is a start vertex, and then plus the cost of this edge, which is 4 to C. So that means we have just found a quote-unquote shortest path to C with a cost of 4. How does that compare to the current stored distance to C? It's smaller, okay, so we have to update. So we have to go to vertex C and say, okay, it's no longer infinity, instead it is 4 at this point. And also, it is not undefined. The previous is no longer undefined, it is now A, because we have just found a way from vertex A to vertex C with a cost or distance of 4. Okay, so that took care of one edge. The other edge is here. So we'll do the same thing. Okay, we go to B and say that we have now known a shortest path with a distance of 3, and it is coming from vertex A. Is that okay? All right. So now we can go back to the outer loop because we have just evaluated all the outgoing edges coming out of A, and also make a little note here so that we remember that A is no longer in the set Q. So we only have 6 vertices left in Q, and out of those 6, which one has the lowest distance? That's the minimum distance. F has the lowest distance. Okay, so let's choose F. So now we have to remember that F is no longer in the set because we have just removed it. And just make a note here that we are evaluating F. This part is really more helpful to you than to me for grading, because this helps you track, okay, which vertices have been removed, which one is still in Q, so this way you can kind of track the algorithm a little bit better. Okay, now that we are looking at F, which is this guy here, it has only one single outgoing edge, okay, which is great. It has one single outgoing edge to C. So now we have to look at C and say, okay, what about this edge here? Did we find a shorter way to get to C than before? And because we are going from F to C, we are considering this edge. We have a known distance of 2 going to F at this point, plus the 1. So now we have found a path with a distance of 3 to C. Is that shorter than what we already know?
Yeah.
It is, okay? So we go to C and go like, oh, we just found a shorter way to get here, which has a distance of 3, but then you have to change the previous, because in order to use the shorter path, we cannot come from vertex A anymore. We now have to come from vertex F.
Yeah.
Sorry?
You wrote C.
Oh, I wrote C, okay. I said one thing and typed something else. Okay. Yep, question?
In that algorithm, would it be 2 plus 1 or 1 plus 2?
It will be a 2 plus 1.
Okay.
Because in the algorithm, I specified the distance to F first, and then plus the edge. Now, obviously, addition is commutative, so it doesn't matter how, what the ordering of the adding doesn't really matter. Okay. All right, so that's the only edge coming out of F. We're now done with the inner loop, which is for each neighbor, and we go back to the outer loop, which is asking, okay, is Q empty? Not quite. It still has 4 elements. So of these 4 elements, B, C, E, and G, which one has the shortest distance? We also have to remember to mark F as no longer in the set, because every time we remove something to become V, we have to remember to remove it from Q. So of all the 4 elements left in Q, which one has the shortest distance? There are 2, okay? There are 2 of them, because B and C, they both currently have the shortest distance of 3, and you are free to pick just either one of those, okay? Just use one. Which one do you want to use?
B.
B? Okay, let's pick B. All right, so here's B, and we look at B and go like, okay, look at all the outgoing edges of B. So let's first note that, okay, Q is now C, G, C, E, G. C, E, G, because B is now removed. So we say B equals B at this point, and we just put a little prime here so that we know that B is removed from Q already. And then we look at the 2 outgoing edges of B. Once again, it doesn't really matter if we look at the neighbor F first or whether we look at the neighbor E. You can pick either one. I'm going to pick E first, okay? So the shortest known distance to B is 3, plus this one is a 4. So we now have found a path of a distance of 4 to E. How does that compare to the current known distance to E?
Small.
It's smaller, okay, because it's currently infinity. So we have just found a shorter way to go there. So it is now a 4, comma 4. And in order to use that path, we have to go from B to E. So the pref, or the previous vertex, is now updated to a B. Okay, very good. And then we have one more neighbor. The other neighbor is F. Okay, so we look at F and we go like, okay, the known distance to B, the known shortest distance to B is a 3. 3 plus 4 is a 7. How does 7 compare to the shortest known path to F, which is a 2? It's longer, so we are not going to update anything. Okay, so we'll leave this 2 alone because the distance known at this point is already shorter than the new path. Okay, so we're done. with that iteration of the outer loop. So now we have to look at C, E, and G and pick one to work with. C has a known distance of 3, E has a known distance of 4, and G has a known distance of infinity. Which one should I pick?
C.
C, okay, very good. So we update Q so that C is no longer a part of the set. And we put a little prime here to basically say that this is also removed. Okay, so we now look at C and look at all the outgoing edges. C only has one outgoing edge to G. Okay, so that's the only one we have to consider. The current known shortest path to C has a distance of 3. So it will cost me 3 to get here, plus the 2 to get to G. So that means it's 3 plus 2, which is a 5. How does that compare to the known shortest distance to G at this point, which is infinity? It's shorter, right? So we go for the update. So now we say this is updated to a 5, which is because of the 3 plus 2. But we also have to update the previous at the same time and say that in order to get to G, we have to go through C. So there we go. And G is, okay, so we got it updated. We only have E and G left, okay? So between E and G, which one has the shortest path?
E.
E has the shorter one because it has a known distance of 4, but the shortest path to E only has a distance of 4, which means that we're going to pick E as the next one. So we update Q so that E is now removed from Q, and the V that we are now considering is vertex E. And then we put a little prime here just so that in the table it is also represented that it's just removed from Q. So let's look at E. It has got 2 outgoing edges. The one outgoing edge is going to A, okay, which is one of the start vertices. But this doesn't stop us from evaluating whether we have found a shorter way. We still have to evaluate it. So we look at E and we go like, okay, the current known shortest distance to E is a 4. 4 plus that 1 is a 5. So we have just found another way to get to A, which is a start vertex, but it has a distance of 5. How does that distance of 5 compare to the current known shortest distance of 0? 5 is more, so we haven't found a shorter way to get to A. Nothing gets updated. Is that okay? But we still have to evaluate it. The other outgoing edge is from E to F, okay? And since the current known shortest distance to E is a 4, 4 plus 1 is 5, and then we compare that 5 to the known shortest distance to F, which is a 2. We haven't found a shorter way to get to F, nothing to update. So now we are down to the last one. Back to the outer loop. We are now taking G out of the set and say V equals to G, and then we also say that G is now removed. So we look at G and say, okay, do we have anything to do here? Well, we actually technically do have something to do because G has one single outgoing edge of this 4 here. So we look at G, which currently has a shortest path of a distance of 5. So 5 plus the 4 is a 9. So now we have just found another path to go back to A with a distance of 9. But A already has a shortest known distance of 0. 9 is obviously not going to be any shorter than 0, so that there's nothing to update. So by the time we get back to the outer loop, Q is already an empty set, and the algorithm concludes. Yep.
So this would work the same with bidirectional graph, right? It just would take longer.
If you have a bidirectional graph, it is the same thing as saying there's a. Let's just take the BF as an edge. That means there's an FB edge that has the same cost.
So we would just have to evaluate more edges.
Yes, a lot more. But in the case of a map, sometimes it's not going to be the same distance. Especially if you drive in a town like San Francisco, there are one-way streets, which means if going one way has a known cost. By going opposite, you can always just make it a really high cost. It's like if I don't get caught by a cop and I do not get into a car accident, I can still go in that direction. It's just going to be a very high cost because the chances of getting into an accident or not actually being able to get through is pretty high. Yep.
Now, this is related but slightly aside. I'm wondering, to deal with infinity, if we were to actually write this out in the program, we'd most likely just get a Boolean for infinity and do a check.
Well, that is a good question, because you can actually have macros in C and C++ to represent the highest value that you can represent using a particular type. Okay, so if you look into C++, constant, maximum, okay, let's just take double as a consideration, okay? So you can, if you look it up, you can still find limits. You can actually find the actual limits as a constant. So you can always use that to initialize the table. Because nothing can be more than the maximum.
Okay, so you would just initialize it to the absolute maximum.
Yeah. So in this case, so when you look up this slide here, which is from C++reference.com, for each type, there's a macro defined to represent the maximum value that you can represent using that particular type. So instead of using quote unquote infinity, you can just use these things to initialize the table, depending on what the type is when you use to create a table. So
that
if you
way,
use,
when it runs the check, it will automatically be.
yeah, it will serve the purpose of infinity,
Yeah.
because nothing can be more than this particular quantity.
Okay, cool.
So you just have to make sure that you have no edges. You have to choose a type that has more range than your highest edge value.
Yeah, the distance of the longest path.
Yeah.
Right. That's correct. Okay, so that's a good question. Because in terms of implementation, you don't have an infinity quantity. Well, the floating point actually does have an infinity. If you look into double, there is an infinity representation, but for integers, there are no infinity representations.
How is there an infinity representation for double?
Ah.
I got it now.
Oh, okay. C++. Okay, I think that should do it. So when you look at C++, there's an infinity quantity. There you go. So this is how you get to the infinity representation of a double. The infinity of a double floating point number is actually specified by the IEEE standard. So when you look at IEEE double precision floating point numbers, the Wikipedia thing is actually pretty good for this one. So if you look up infinity, there's an actual bit pattern to represent infinity for a double precision floating point number. So they designate a particular bit pattern to say, yes, this is infinity.
So that's cool. It's standardized
It is completely standardized. This is an IEEE standard.
and negative infinity.
There's an infinity and also a nan, which is not a number. Nan stands for not a number.
There's a -0 above there.
There's a -0 because it uses one particular bit to represent the sign of the value instead of using 2's complement. That's something that we talk about in CISP 310. So instead of using 2's complement, it does use one bit to represent the sign of the quantity. So the quantity 0 now has a plus, it has a has a positive 0 and a -0 because of the sign. But we normally do not like to deal with double because it's kind of expensive to deal with math in double. Okay, all right. So are there any other questions? No other questions? Okay, so without any additional questions, now it is time to create the solution. Okay, so let's go back to the algorithm itself. So the solution is to define a new graph where we only use the prev, okay, the previous function, to designate the edges in the solution E prime. Okay, so we can just go ahead and modify or highlight this graph here. So what I'm going to do is I'm just going to copy this graph here to the solution area. Well, actually, I have it done already. This is one of those Ron Koh show, like, well, we'll put it into this often But I have it prepared ahead of time, so it's already done, and the audience can have a piece. So this is the solution, okay? But if we don't want to look at this solution, we can always just, actually create it. So I'm pasting it in here.
So do you just end up leaving out the edges that make for longer paths?
Well, this is what we'll do. Okay, I'm just going to change the color. In other words, we look at all the prefs, okay, and then every time we see a vertex with a pref, we will update that particular edge using a different color. Okay, so we look at A. Okay, A does not have a pref. Why doesn't it have a pref? Why is it still undefined?
This is a start point.
Because it's one of the start vertices. Okay, it doesn't have an edge in the solution to go to it. Okay, so that makes sense. Let's look at B. B has a incoming edge from A. So the edge between A and B, which is this one here. Okay, I'm going to change the color. And we'll just change it to red. Is that visible to you guys? Okay, it's good. Okay, cool. So that's one. And then we look at C. C got updated twice. Okay, if the first update is from undefined to A, and then the second update is from A to F. But the current value, the last value, is F. So to go to C, we have to go through F. So to go to C, we have to go through F. So that means this particular edge is the one that we want to update. It broke it up into two halves. I guess because it's a curve. So we'll update both of those halves to red. So there you go. And then we look at D. D is one of the start vertices. It does not have a pref. And E has a pref of B. So to get to E, we have to go through B, which is this one edge here. Okay, so we change the color of that one. And then for F, we have to go through D. So F is over here, and D is over here. So this edge is the one that we need to update to a red color. Where's my color tool? Where's my color tool? Oh, there we go. I have to highlight it first. There we go. Okay. And then G is coming from C. So G is coming from C, which is this edge here. So we'll update that one. So the red ones are now representing the solution of this particular graph. They are representing the edges of the shortest paths from A start vertex to each of all of the other vertices. Are we doing okay so far? So to kind of make this a little bit even more visible, I can go ahead and delete all of the other ones. So all the ones that are not in the solution, I'm just going to get rid of those. Okay, how do I get rid of this? There we go. So now what is left here is the actual solution. Okay. There we go. So this is the actual solution. Now in this class, we didn't quite have time to go through spanning tree and stuff like that. But this is also a minimum spanning tree, which is basically a tree of edges that only consists of edges to the solution. And it's also guaranteed to be a tree. In other words, there are no vertices here that will have two incoming edges. That's guaranteed. And why do you think that is the case? That's actually one of the other questions. But since since I'm on this one, why do you think there are no two incoming edges to a particular vertex when you look at the solution of shortest paths? What would that imply when you have two incoming edges to a single vertex when you are only looking at the solution?
Wouldn't that mean both paths had to be the same?
Right, but how do we represent it? When you look at the Dijkstra's algorithm, how does it represent the solution? How come I know which edges to mark as red in this case?
From the previous.
From the previous, okay, very good. So a previous is basically saying, okay, it's an incoming edge, an incoming vertex, right? It's representing an incoming edge from another vertex, right? How many prefs can I have for each vertex? It's only one. Well, that answers that question, doesn't it? All right. So, do we have any questions about this one? How to trace and what the algorithm does? questions? Alrighty, so we can download as, okay, I'm done editing, so I think there's a way for me to say it's all done. Yep, I just couldn't see it. There we go. All right, so when you look at, they're identical, okay? I just worked on this one live, just so that you can see how the edges are created in the first place. Okay, this is question number 2. For a directed graph, okay, G equals VE, I don't know why that one is a particular problem, because I can have anything else, just not, that. Okay, G, see, once I type G, it knows what it is, but once I remove the G, it says it's an error.
Just like a prime apostrophe or something.
What if you just put a space in front of it?
Yeah, I'm putting a space here, and it's okay.
There you go.
But that is just weird. I mean, this is, it doesn't make any sense. It bugs me. Okay, so G equals VE is a, sorry?
I said maybe you stumbled upon a code and the syntax is just slightly off.
No, I'm pretty sure the syntax itself is not a problem. It's something else that's causing that quote-unquote error to happen.
I mean like a code that wasn't obvious and specified.
Well, because I can do this one more time and it will still come out as an error, but I can have any other equation. So I can say G equals VE, and the moment I close the parenthesis, it will turn into error. It's very predictable. But if I, just like what I did a little bit earlier, if I do a space, oops, I have to go into the equation first. There we go. If I put a space first, then it's okay. If I put a space anywhere, it's okay. I can put a space probably at the very end, and it will still be okay. So this is a weird one. I cannot explain this one. Okay, so for a directed graph, G equals to VE, and the associated edge cost function is C, which maps all the edges to real numbers. Okay, so when I say C colon E to R, it means it's a function. This is from the function terminology. So C is a function mapping E to R. Given that for all edges in E, C of E is greater than 0, in other words, we don't have any cost of edges that are negative or 0, prove that all walks are paths in the Dijkstra's solution graph as computed in the modified Dijkstra's algorithm. And the hint is to use proof by contradiction. Note that the structure of the proof is important, as are the steps in the proof. You have to think of cases where a walk is not a path and use proof by contradiction to show how that is not possible. Okay, so that means the first thing you need to know is what is a path in graph theory. A path is one that does not have you cannot have a vertex appearing more than one time in the path. Is that okay? All right? Okay. So what I want you to prove is, every single path in the solution, which is G prime equals to V and then E prime, every single path over there is, every walk is a path. Okay, I have to go back in and say all the walks are paths. A walk is basically just a sequence of vertices by following the edges, consecutive, adjacent edges. So if you take any walk within the solution, it cannot be a non-path. It has to be a path, which means the same vertex cannot appear more than once within that walk. Okay, so why is that the case? So I want you to prove it by contradiction. The solution is actually here already. I was too lazy to want to retype it in class, so I'm just going to show you. I changed the color of the text to white, so it's not visible. So by changing it back, okay, where's my color tool? Probably under more. No, where's my color tool? Text color. There we go. Ding. Now they're back. Okay, so the answer is kind of long, but I do want to show you the entire solution. Okay. Now the solution does not even, the proof does not even use the fact that Dijkstra's algorithm always find the shortest path. Okay, because if you say that the solution of Dijkstra's algorithm is always finding the shortest path, then it makes sense that you should not have loops. Is that making any sense? Why not? Okay, I know it's intuitively true, okay, but let's find out why that is the case. So let's say that I want to go from, this is vertex A, this is vertex B, I want to get to vertex C, okay? And let's just say that the walk inside the solution of this Dijkstra solution is a loop, okay? So I can go here and then back to A and then go to C, okay? Why is this should not be possible when all the edges are represented as they're all on the shortest paths?
Because A to C is always going to be shorter than A to B to A to C.
Exactly. Okay. In other words, anytime you have the same vertex appearing more than once in a walk, you can just snip it, and that becomes a shorter path. Okay. Let me give you another representation. So let's say we have a walk, A, B, C, B, and then back to B, and then E, F, G. Okay. So this is a walk, and if I know that the paths are, the edges are from the optimal solution, so that means in here I can snip this section altogether. In other words, I can go A, B, E, F, G, and get to the destination. All this stuff here in between the B, C, D is extra, and because I know the edges have non-negative, they all have positive costs. I know this path, okay, including B, C, D, is going to be longer compared to A all the way to B and then E, F, G. So without even using that fact, how do we prove it? It's a really easy one, okay? So the walk, so it has to do with each vertex in the solution only has one pref. Remember what we talked about earlier? For each vertex, there's only one incoming edge to each vertex in the solution graph. So in that case, the case one is the tour can involve at least one start vertex. In this case, the tour should never be formed because the distance to a start vertex is 0 itself, so there should be no incoming edge to a start vertex. Okay? So case 2 is the tour can be detached or disconnected from any start vertex, and this is also not possible. Now how can a tour be detached from any start vertex in the solution of Dijkstra's algorithm? It cannot, because everything has to be attached eventually to a start vertex. Is that making any sense or not? Okay, so let's do this. Okay, so we can go through this proof here. So what we want to do first is to say that for all vertices in V, the distance of V being not infinity implies RV, where RV means the R is reachable from a start vertex through a walk. In other words, it's not detached from a start vertex. And this can be done by induction. So we are now combining proof by contradiction with proof by induction. So the base case are the start vertices, because each start vertex has a distance of 0 based on the initialization, and each start vertex by definition is reachable from itself. Okay, so we cannot have start vertices that are detached from start vertices. That just does not make sense at all. But that's our basis. That's our base case. The induction step is based on the steps of the algorithm of how we update pref and dist. So let's switch back to the algorithm itself and see how we update dist and pref. Okay, these are the only two statements other than the initialization that can touch distance and pref, the previous vertex. Is that okay? There are no other assignment statements that can update these. How did we get here? Well, to get here, we have to first meet this requirement, okay? But more importantly, there has to be an edge in the original graph to go from a vertex V into the vertex W. In other words, there's something connected to W in order for W to be updated. Is that okay? What about this V here? Well, how did we get this V? This V is chosen because it has the lowest distance amongst all the vertices in Q. Is that okay? Now, how do you choose how did V end up with a distance that is not infinity? It got updated. And because this is proof by induction, how do you use proof by induction? There's the base case, and then there's the induction step. What is the first thing you need to state in the induction step? We assume the theorem is true for cases up to a certain state, and you're just working with the next one, right? So when we look at the proof, we are basically assume at some point of the execution of the algorithm, we already know this is true for a certain number of vertices. So by choosing another vertex V from Q, assuming the theorem is true for all of the other vertices already, so by induction we can prove that there's a way to get to V already from a start vertex. Now that we can connect vertex V to vertex W, it also means that vertex W is reachable from a start vertex. And that completes the induction step. Is that okay? Okay? Now, you also have to be careful to know that this is an implication. It doesn't say that every single vertex is reachable. It simply says that if a vertex has a distance that is not infinity, that means it is reachable. Now, why do you think it is important to have that implication? I'll give you one example, okay? Just using the whiteboard. It's an easy one. So I have a start vertex A, okay? And I just have another vertex B here. There are no edges. Okay, so let's look at this one. So I'm going to say this is a start vertex, and this is a vertex B, which is not a start vertex. So how would the algorithm work in this case? I mean, would it work? Would it get into an infinite loop, or would it seem it was still complete, but it will have some kind of weird, kind of strange result? Let's think about this one. Great. Well, it says right here, try erase. Because occasionally some professors would use the wrong marker. Okay, this is why I don't use whiteboards. Probably pick a different color and see if it works better. Okay, so if you look at this one, and you have, the vertices, right? Vertices. We have A and B here. We have prev, the previous vertex, and then we also have distance. And the initialization of this one is going to have a 0 for A because it is a start vertex. And then both of the previous are undefined to begin with. And then B has a distance of infinity to begin with because it is not a start vertex. So this is the initialization. Dijkstra's algorithm would go through the Q, which initially has both Q and with A and B, pick out the one that has the smallest distance, which is going to be vertex A, right? So V becomes A, and then we say, okay, let's look at all the outgoing edges of A. A has no outgoing edges. Okay, it's just a vertex that has no connections whatsoever to everything else. So it's done. So Q is now B. Now, when Q is B, what do? We still ask the same question. Which one has the shortest distance in Q? Well, you don't have a choice. It is B. So you still have to pick, this to be B. So Q is now empty. So we now look at B and go like, okay, let's look at all the outgoing edges of B. B has no outgoing edges, right? So there's nothing to do. So that means, the initial state of prev and distance remains as it is when the algorithm completes. Is that okay? So the theorem over here is saying that for every single vertex in B, if the distance is not infinity, it means the vertex is reachable from a start vertex. Is it still true? Does it still apply to vertex B? Yep, because vertex B does have a distance of infinity, so whatever is on the second part of the implication does not need to apply to it. Is that okay? So that's kind of little fine points that are important. So with this particular smaller theorem proven, it means we cannot have tours that are unreachable from a start state. So everything has to be connected to a start state. This is because for each vertex V in a tour must have an incoming edge that is not a start vertex itself. However, having an incoming edge means pref is set. In the algorithm, the code that updates pref is also updating distance, but we already know that distance only updates when the new distance is not infinity, because we never update a distance that is infinity to something that is not infinity. And a distance of less than infinity implies the vertex is reachable. And since a walk that has a repeat vertex can only be a tour, we cannot have a tour that includes at least one start vertex. Because if you have a tour that includes a start vertex, that means you can cut out whatever is in between. Is that making any sense? Okay, let's just draw that picture here. Okay. So let's say we have A, B, C, D, E, F, G as a walk. Okay? But in this walk, there are two start vertices. A obviously has to be a start vertex, but let's just say that, I don't know, D is a start vertex as well. Just like in our example. Okay, we got two start vertices. Well, if this is a claim to the shortest path, it's not. Because D is already a start vertex, I can just do this too. That becomes a shorter path because the edges have non-zero positive costs. Does that make any sense? So you cannot have a tour with multiple start vertices in the tour. Or any walk with multiple start vertices should not be possible. Okay, so that's the end of this proof. I'm not expecting you guys to be this detailed, but you have to be moving in the correct direction. Okay, so you have to give me arguments of about the same kind of rationale. Question number three. Question number 3 is to refer to the graph of G of Q1. So I'm reusing that graph several times. In this case, I want you to draw a subgraph. In other words, pick out a subset of the vertices and a subset of the edges so that you can show me a path that has 5 vertices. Now, this is not referring to the solution. This is only referring to the original graph. So let me pick out the original graph from one of the, I guess this one is good. Okay, so pick out one path, which means it cannot have repetition of the vertex that has 5 vertices. Hmm?
Say at least 5.
Exactly 5. So you can go from D to F to C to G to A. I think that's 5. Yep. So that's one path that has 5 vertices. Sorry?
A to G.
A to G.
You got A to B to E to F to C.
Yep, that's another one. Yep, there are several solutions. Okay, very good. So let's look at the second one. A tour means something one vertex has to be repeated. At least one vertex has to be repeated. That is the longest. The start and the last vertex are the same, and that makes it a loop. Okay. So a tour that is the longest. Note that there may be multiple tours of the same length. Just use one of them. Okay. So let's pick out a tour that has the longest distance within the tour itself.
We'd have to start with A, right? Because that's the only thing that comes back to itself.
Well, there are several things that are involved in loops. E is in the loop too. But you have to pick out the one that has the longest distance,
Okay.
not
You
the
don't-
most number of vertices.
You don't have to start with a start point.
Nope, you do not have to start with a start point. Okay, I think G to A to B to F, back to C, back to G, that one is the longest.
Instead of doing B to F there, go down to E and then to F.
B to F and then to...
No, that'd be shorter.
What are those two? Are you counting the distances?
We are counting the summation of distances, the length, not the number of vertices.
Oh, okay.
Yeah. Yeah, I should make it more clear. It is the sum of the distances that I'm looking for, not the number of vertices that I'm looking for. Yep. But you guys know the concept, right? The idea is to just pick out the longest one, so you can start with the larger numbers. Typically, that will give you an idea of what is the longest. Okay. Next one, a trail that is not a path. So now you have to know what is a trail. A trail is one that has no repeating edge. A path has no repeating vertex. So we're looking for a walk that has a repeating vertex but no repeating edge. That's an easy one.
Just do a little loop.
Yep, just a little loop. So this one would do.
Well, next to it too.
Yep, this one would do too.
And next to it.
And it doesn't ask for the longest one, so you can just pick whatever is the most convenient. The order of the graph, okay, the order graph is 7 because you just have to know what is quote unquote the order. When it comes to the order of a graph, it means the number of vertices, or the cardinality of V in this case. The size of the graph is the number of edges, or the cardinality of edges. In this case, it is 10. These are the solutions. These are the answers to those questions. Okay, are we doing okay so far with these? These are mostly just related to the definition of terms related to graph theory. And then we have question number 4. Question number 4, once again, okay, fix this error here. G equals to VE with a space after, and it won't complain them anymore. But this is really weird. Oh, okay. All right, so we'll just have a space over there. Fine. Okay. So in the directed graph G equals to VE, define a relation R. Okay, do you guys still remember relations? Okay, relations are just is just a subset of the Cartesian product of V and V itself, such that for all V and W in V, V are V if and only if there is a walk from V to W. So not edges. In this case, I'm using, if there's a way to walk from V to W, then V R W is true. Is that okay? So R is basically reachable. Okay, look at R as reachable. Is W reachable from V? Populate the example column of the following table with graphs with at least 2 vertices. For each case that is not possible, explain why it is not possible. Okay, so let's take a look at these 3 columns. Okay, these are already preset for you. You just have to give me an example that corresponds to this. So in the first case, I did something that is reflexive, symmetric, and transitive. So you have to give me a graph, that is reflecting these. Okay, what is reflexive? So we have to first remember, relations definitions. What is reflexive? Okay, so let's go ahead and make sure that we remember what is reflexive.
Reflexive means X, R, X.
For all vertices, for
Yeah.
all things
So-
in the set. Okay, so let's go ahead and say reflexive is, and then I'll use the math equation here. Okay, for all V in V, uppercase V in here, VV is in relation R.
So
Okay.
Equal to?
Hmm?
Equals? Is that
Yeah, equals to is reflexive. But in this case, we are dealing with whether a vertex is reachable from itself. Okay, so that's reflexive. Okay. What is symmetric? Symmetric is, now in symmetric is a little bit more tricky because it does rely on implication. Okay. For all, and in this case we need two vertices, V and W, in uppercase V. What needs to be true in order for a particular relation R, in this case, to be symmetric? To use the relation notation, VRW implies right arrow WRV. That's symmetric. Is that okay? It simply means if I can walk from V to W, I should be able to walk from W to V in the context of a graph and walks. Okay. What about the last one, transitive? Transitive is what?
Is that A R
This-
between BRC implies
Yep. Implication is involved here as well. So we say for all V, W, and X, because we need three elements in this case. In V, we have to use implication, right arrow. And if you can show me that VRW is in the relation and WRX is also in the relation, not to be affiliated with Subaru or anything like that. Okay, very few people know what it is. Fine, good. Huh? So it has to imply VRX. Okay. If I choose C instead of V, then we can have a Honda models. Okay, so given these are the definitions of reflexive, symmetric, and transitive, give me a graph. Okay, so G is a graph. G is a graph. Show me the vertices and also the edges that can kind of like the minimum that can make this happen. You can draw the picture too if you want to. So since I'm not really good at drawing pictures using Google Documents, I'm just going to use this kind of longish representation. So the simplest one that can make this happen to be reflexive, symmetric, and also transitive is to use a loop. Okay, anything that has a loop, will work. So I can just pick, 2 elements would work, but 3 makes it more obvious. So the vertices would include A, B, C as vertices, and then the edges would include an edge from A to B, an edge from B to C, and an edge from C to back to A, and that will do it. Okay, let's double check. Okay, because I'm only considering walks in this case, I'm not considering edges. In other words, I do not need an edge from A back to A. I just need to be able to walk from A, eventually ending up to A. So when I have these edges, to get back to A is easy. I go A to B to C, and then back to A. What if I start with B? Well, it's a loop. You can start at any point and get back to that very same point. So it is reflexive. Okay, I can walk back to the same vertex. Okay, what about symmetric? If I can walk from A to B, does it imply that I can also walk from B to A? Well, I can just use the other half of the loop to go from B back to A. So it is also symmetric. Is it transitive? If I can go from A to B, and I can go from C to B to C, I can go from A to C. So it is also transitive. So that means it is satisfying all 3 requirements in this case. Okay, the next one is tricky because the only thing it does not want you to, doesn't want to have is transitive. Can you have a graph that is, in terms of R being walkability or reachability, that is not transitive. That is not possible. Okay? Okay? It's simply not possible regardless of how you make your graph. Okay, so you need to briefly explain why, okay? Because you have to say that if there is a walk from A to name some other vertex B, and there is a walk from B to C, then there is always a walk from A to C. You cannot make it non-transitive. Well, that handles, you can say this is note 1. I would do this in an exam too, to save you time. You can just say this is note 1, which is the explanation of this case. And then for everything that has transitive being false, you can say C note 1. Well, that can help you save you some time in the test. And I have no problem with this as long as you make it very clear where is note 1. Yep.
Wouldn't it be one of the first two relations that implies that we can walk from A to B and from B to C?
Say that one more time.
Wouldn't it be either the reflexive or the symmetric relation that is telling us that we can walk from A to B and from B to C?
No, reflexive doesn't automatically imply doesn't always automatically imply transitive. Because you can have an edge going from A back to A, that makes it reflexive. But in this case, because it's a graph, there's no way to make it not transitive. Because if there's an incoming edge to vertex B, and there's an outgoing edge from B to C, then you complete the path. There's no way to make it not transitive. Okay. You can prove it by contradiction too. You can say that let's make a graph that is not transitive and see what kind of weird things you can say about it. Let's see, how much time do we have? We are running out of time already. Okay, so I'm going to finish this and give you the whole solution on Wednesday. Okay, so there's one more question down here, so we'll finish it on Wednesday.
When is the final?
The final, I believe, is next Monday,
Really?
and that's why I have to talk about the practice test today because it's 1 week before the final.
So tomorrow or Wednesday's our last class then, huh?
Wednesday is our last lecture. Yep. Yep. Time flies.
Still thought we had a couple weeks.
I wish we had a few